till now we have completed introduction part, Euclid's division, lemma, algorithm, and then fundamental theorem of arithmetic. Till now we have completed all these topics, and today's topic we are going to learn into a new topic, that is revisiting irrational numbers. Okay, to get started we just have to brush up with few basic concepts. In real numbers, as we have discussed earlier, there are two parts. That is, one is rational numbers and the next is irrational numbers. What is rational number? Any number which is in the form of P upon Q, where Q is not equal to 0. What is rational number? Any number which is in the form of P upon Q, where Q is not equal to 0. Few examples: 1 by 3, 2 by 7, 22 by 7, etc. What is irrational number? For irrational number there is no proper definition as such. For rational number we have this, which is of the form P upon Q, where Q is not equal to 0. But what is irrational number? Irrational number, according to your textbook only, it is defined as irrational number is a number which is not rational number. So for these examples can be root 2, root 3, pi. Here if you can observe, I have written 22 upon 7 here and I have written pi over here. What is the value of pi? 22 upon 7 is the value of pi. But here 22 upon 7 can separately take an example for rational number, while only pi, which is not elaborated, that is, we cannot write this as 22 upon 7 here. We can write here, but you cannot just write 22 upon 7 and name that as a rational number. If you have just considered 22 upon 7, you have to consider that as an rational number. If you write this, denote it as pi, you can write it as irrational number. Okay, these are few examples. If you can observe, all that I have written is, under the root I have written prime numbers. 2 is a prime number, 3 is a prime number, 5 is a prime number. Any number which is of any prime number is an example for irrational number. I have taken this particular example because in the coming topic you have topic related to this only. To get started, we have this one theorem. Using this theorem you have questions based for 3 marker. So what is the theorem? What does the theorem say? First let's just read the theorem, then I'll explain it by myself. Let P be a prime number if P divides A square, then P divides A, where A is a positive integer. If you just read this, nothing will make sense for you. So I'll break this. So what is given? Given is that P is a prime number and A is a positive number. Here A is a positive integer. If P divides A square, we should prove that P divides A. This I have given in a statement. I have broken down the same parts and given you in a friendly manner that what is that they have given. They have already given that P is a prime number. P is a prime number. What are prime numbers? 2, 5, 7, 9, 2, 5, 7, 11. All those are prime numbers. A is a positive integer. Prove that if P divides A square, we have to prove that P divides A also. So how should we even start this? Proof. Given A is a positive integer, we'll consider this positive integer as a composite number. You know what is composite number? Number which is divisible by 1 and more than 2 coprimes. Given that A is a positive integer, I'm writing all the statements so you have to understand. So if A is a composite number, how can we represent A as? A can be written as P1 into P2 into P3 into Pn. We don't know what composite number we have actually taken. It can be any number, any infinite number. So only we have, using this fundamental theorem of arithmetic, using fundamental theorem of arithmetic, what is composite number according to fundamental theorem of arithmetic? According to fundamental theorem of arithmetic, a composite number can be shown or represented as a product of primes. So here we have taken A is a positive integer, that is composite number. We don't know what exactly is a composite number. For example, if we had taken number 9, we could have written this as 3 into 3. If we had taken 12, 2 into 3 into 2. We could have, for example, if this was the case, if we had taken number 9, we could have represented it as 3 into 3. If we had taken 12, we could have written as 2 into 3 into 2. We have not taken exact number over here. In case we had a certain number, we could have represented that as a product of primes. But here in this case, to prove this theorem, we have not taken any numerical example. Using the alphabets only, we have to try and solve. So here, since no number has been taken using variables, for your reference I am writing that since no number has been taken using variables, if this A is a composite number, how are we going to represent? P1 into P2 and P3. What are P1, P2, P3? These are prime numbers. P1 is also a prime number, P2 also is a prime number, P3 is also a prime number. It goes on until Pn. So all these are prime numbers. So we need to get this A square. What should we do that? Square on both sides. If we square on both sides, A is equal to P1 into P2 into P3 Pn. This was what was there, and we have squared on both the sides. We'll be getting A square is equal to P1 into P2 into P3 the whole square. We have got this, and we have to elaborate the same. So if we elaborate, we'll get P1 square into P2 square into P3 square Pn square. This is how we can write. So further, if we want to write, A square is equal to P1 into P2 into P3 into Pn. The whole thing, I am writing this as twice here. Since it is square, this into multiplied by something gives you the whole square, right? So I am writing the same thing twice. Again P1 into P2 into P3 into Pn. Okay, till now what I have done over here, first we have considered that A is a positive integer and it is a composite number. Then to prove that, since we have not taken any numerical example, we are just considering that A is a composite number, and any composite number can be represented as a product of primes. So product of primes P1, P2, P3, all these are prime numbers. So we are showing that and represent that in a product form. Since in the question we need that P divides A square, we are writing that we are squaring on the both sides and we are considering the whole thing. If here P1, P2, P3 all are prime factors, right? So P1 here, if we consider any number, say P, 625 is there and 5. This is a number, okay, 625 we have considered. This is 25 upon 5. See, the whole thing 5 is something which is divisible by 5. 625 is a number that is already divisible by 5. Even if we just take a square root of that, we'll be getting 25. 25 square is 625. If we take square root of that, we'll be getting 25. Here 5 square, 25 is divisible by 5. See, 625 is a number which is divisible by 5. Hence the whole number 25 is also divisible by 5. This is a numerical example. Based on this, now we are trying to write this. P is a factor of A square. Hence, P must be a factor of A. That implies if P divides A square, it has to satisfy P divides A. Let me explain what I have written over here. Till here I hope you have cleared. A square can be represented as the whole thing. This is A set and A set. Okay, since we have considered A already, we'll consider X. The whole thing we are considering as X, and here also X. X into X is X square only. This thing we are elaborating in this and this manner. Here we have taken an example 625. 625 is a number which is divisible by 5. If we can observe, 5 is a factor of 625. Hence even 25, 5 is a factor of 625 also, and 5 is a factor of 25 also. First, since 625 is divisible by 5, hence 25 is also divisible by 5. Using this numerical as a basis, we are trying to prove this theorem. Here P1, P2, P3 are all prime factors. P is a prime factor of A square. This is all. See, P divides A square. P divides A square is nothing but factor of A square. Okay, it is already given that in the question P divides A square. So, since P is a factor of A square which is given, hence P must be a factor of A. That implies that if P divides A square, it has to satisfy P divides A. Now in a one slide, I'll just sum it up again once for you. Let A be a positive number. So we'll consider that positive number as composite number. Composite number can be represented as A is equal to product of primes P1, P2, P3, Pn. So if we just square this on both sides, what we'll be getting is A square is equal to P1 into P2 into P3 into Pn the whole square. This can be again represented as A square is equal to P1 into P2 into P3 Pn into P1 into P2 into P3 into Pn. So all that we want to know is P square. P divides A square. This A square should divide P. So let's divide this by P and the whole thing by P. Here using this example, I have already showed you this, that this is a factor of this. This 5 is a factor of 625 and this 5 is a factor of 25 also. Here P is a factor of this also and this also. This P can be cut over here also, or this P can be cut over here also. It can, since this is a prime factor, this can consider anything. P1 also is a prime factor, P2, P3, P par n, anything is a prime factor. Since this cuts this, we can write that since P is a factor of A square by fundamental theorem of arithmetic, it is also proven that P is a factor of A. See, this is one way to represent your answer in a theory question, or these two slides. If you start like this thing is common. This given and prove that you have to write in either of the ways, or if you can start, this is one method where you can write proof, you have to write all these two slides also you have to write, or if you want to write that given that and proof, to prove you have to write, and this method you can follow. Usually this is the method usually people prefer to, but both remains the same. The only thing is composite number can be represented in the form of product of two primes, where we'll consider the primes as P1, P2, P3 are considered as primes. Since this P is a factor of these numbers, it can also be a factor of A. That is what we are trying to tell, and that is what we have written in a statement form. Let's take a numerical example. We have taken A as 20 and P as 5. Will not write any statements over here. This numerical example is purely for your understanding. So A is 20. Is A divisible by 5? How can A be written? 2 into 5 into 2. This is how A can be written, right? So squaring on both sides. Square on both sides. We'll be getting A square is equal to 20 square, that is A square is equal to 400. Right, this is what you'll be getting. How can we represent this 400? 2 into 2 into 2 into 2 into 5 into 5. Use this factorization method. This is what the prime factors you'll be getting. Since this A square, we have to see that A square upon P. Here A square we have considered it as 20. Here this P is 5. We have to see that this whole thing is divided by 5 or what? That is 2 into 2 into 2 into 2 into 5 into 5 upon 5. This 5 and this 5 gets cancelled. Obviously it is showing that according to this we have proven that P divides A square. Now we have to prove that P divides A also. A is 20. So A by P is equal to 20 by 5. How can 20 be written? Here I have already written 2 into 2 into 5 upon 5. 5 and 5 gets cancelled. Hence P divides A. See, this is how, using a numerical example, I have written. Whatever I have written in a statement form, I have used a single example, that is A as 20 and P as 5. Using this theorem, this example I have solved. A is 20. A is 20 and P is 5. First thing what we did was find the factors for 20, that is 2 into 5 into 2. Then square it on both the sides. We'll get A square is equal to 20 square. So we'll be getting A square is equal to 400. 400 can be written as 2 into 2. These are the factors. 2 into 2 into 2 into 2. 2 power 4 into 5 square. Okay, you have to see that the theorem only is asking us to know that P divides A square, then P divides A. If P divides A square, we have to prove that P also divides A. 400 is divided by 5. So we should prove that 20 is also divided by 5. Hence, using this example, we have proven one. This is a numerical example, but theorem is this. Usually you will be not asked to solve this theorem only as for 3 marker. You will be asked such questions.